Look up at the night sky. It feels calm, silent, almost still. But that feeling is an illusion. Because right now, at this exact moment, our galaxy is moving. The Milky Way is not drifting randomly. It is not standing still. It is being pulled. Pulled at more than 600 kilometers per second towards something we cannot see. Not a planet, not a star, not even a single galaxy. Something far larger, something hidden, something powerful enough to influence hundreds of thousands of galaxies at once. Astronomers gave it a name that sounds almost mythological. They call it the Great Attractor. And the disturbing part is this: we didn't discover it by seeing it. We discovered it because everything around us was moving the wrong way. Galaxies were drifting off course. Clusters were leaning toward an unseen direction. The universe itself appeared to have a preferred flow, as if space were sliding downhill toward a destination no telescope could clearly observe. Imagine floating in a dark ocean. You see no waves, no current, no wind, but everything around you is slowly drifting in the same direction. That's what astronomers noticed. The motion wasn't subtle, it wasn't noise, it was consistent. Galaxies across vast regions of space were being drawn toward a single point in the sky, a region hidden behind the dense dust and stars of our own Milky Way, an area astronomers call the zone of avoidance, a cosmic blind spot. And behind that blind spot, something enormous was waiting. At first, scientists assumed the explanation must be simple. Maybe our measurements were wrong. Maybe the universe wasn't expanding evenly. Maybe local gravity was distorting the data. But as observations improved, the problem only became worse. The motion didn't disappear, it became clearer. Galaxies weren't just expanding away from each other after the Big Bang. They were also flowing sideways, streaming, falling, being pulled. And the deeper astronomers looked, the more unsettling the picture became. Entire galaxy clusters, each containing thousands of galaxies, were all moving toward the same invisible destination. This wasn't a small anomaly. This was a cosmic-scale event. Something with the mass of tens of thousands of Milky Ways had to be responsible. But no single object was visible. No blazing light, no massive beacon, no obvious source of gravity. Just motion. Silent, undeniable motion. Think about that. Gravity is the weakest of the fundamental forces. Yet whatever lies in that hidden region is strong enough to override the overall expansion of the universe, at least locally. Strong enough to bend the paths of galaxies across hundreds of millions of light years. Strong enough to affect us. Because yes, the Milky Way is part of this flow. Our galaxy is moving toward the Great Attractor too. Along with our neighboring galaxies, along with our entire local group. We are passengers in a cosmic current, and for a long time, we didn't even know it existed. The question is not whether the Great Attractor is real. The question is, what could possibly have enough mass to do this and remain almost completely hidden? Because whatever it is, it doesn't just pull matter. It reshapes our understanding of how the universe is structured. And once scientists began tracing this motion backward, following the direction of the pull, they realized something even more unsettling. The Great Attractor might not be a single object at all. It might be part of something far larger, something that defines our place in the universe itself. And once that realization set in, everything we thought we knew about our cosmic neighborhood began to change. Prepare yourself, because the first real clue doesn't come from what we see. It comes from how fast everything is moving. The first real clue didn't come from images. It came from speed. In the mid-20th century, astronomers believed they understood how galaxies moved. The universe was expanding. Galaxies were flying apart. The farther away they were, the faster they receded. This relationship was clean, predictable, elegant. But when scientists began measuring galaxy motions more precisely, something didn't fit. Some galaxies weren't just moving away from us, they were drifting sideways. Others were speeding toward a direction that had nothing to do with Earth. Their velocities contained an extra component, a peculiar velocity, a motion that shouldn't exist if expansion were the only force at work. At first, the numbers were dismissed. Maybe the instruments were inaccurate. Maybe local gravity from nearby galaxies was distorting the data. But the pattern refused to disappear. As telescopes improved, the anomaly became undeniable. Galaxies across an enormous region of space, spanning hundreds of millions of light years, were all moving in roughly the same direction, not randomly, not chaotically, but coherently, like leaves carried by a hidden current beneath still water. This wasn't the motion of individual galaxies, it was the motion of entire galaxy clusters. Clusters containing thousands of galaxies each, and they were all falling toward the same region of the sky. Astronomers mapped this motion carefully. They plotted velocities, directions, distances, and when the data was overlaid, a shocking image emerged. Our local group of galaxies, including the Milky Way, was moving at over 600 kilometers per second relative to the cosmic background. That speed was too high to be explained by nearby matter alone. Something far more massive had to be pulling on us, something far away. But when scientists pointed their telescopes in that direction, they ran into a problem. The Milky Way itself was in the way. Dense clouds of dust, gas, and stars blocked visible light almost completely. Behind that obstruction lay a region astronomers rarely studied because they couldn't see into it. They called it the zone of avoidance. And unfortunately, that's exactly where the motion was pointing. It was as if the universe had hidden the answer behind a curtain. But astronomers didn't stop. They switched wavelengths: infrared light, X-rays, radio waves. Each could penetrate dust better than visible light. And slowly, piece by piece, the darkness began to thin. What they found was staggering. Not emptiness, but density. Behind the Milky Way's glare lay a vast concentration of galaxies packed tightly together. Clusters stacked upon clusters, structures so massive they warped the surrounding motion of space itself. This region wasn't subtle. It was one of the densest concentrations of matter in the nearby universe, and it sat almost exactly in the direction the galaxies were falling. Astronomers realized they weren't looking at a random anomaly. They were seeing the gravitational fingerprint of something enormous, something that had been shaping galaxy motion for billions of years. They named it the Great Attractor, not because they knew what it was, but because they knew what it did. It attracted, relentlessly. And the deeper scientists analyzed the motion, the clearer the influence became. This force wasn't localized. It wasn't pulling only nearby galaxies. Its reach extended across a region of space more than 500 million light-years wide. Entire superclusters were drifting toward it, like iron filings aligning around a hidden magnet. But here's where the mystery deepened. Even the visible mass in that region, massive as it was, didn't seem sufficient. The gravity calculated from observable galaxies fell short. It couldn't fully account for the velocities being measured. Something was missing. Either astronomers were dramatically underestimating the mass, or there was far more matter there than they could see. Matter that emitted no light. Matter that revealed itself only through gravity. The implication was disturbing, because if invisible matter dominated that region, then the Great Attractor might be only the surface of something deeper. A structure hidden not just by dust, but by the very nature of reality itself. And as scientists followed the flow of galaxies even farther, they realized the pull didn't stop where they expected. It continued, Beyond clusters, beyond walls of galaxies, beyond familiar cosmic landmarks. The Great Attractor wasn't an endpoint. It was part of a much larger current, a galactic river carrying entire regions of the universe along with it. And once astronomers understood that, they were forced to confront a new idea. We weren't just falling towards something, we were embedded inside something vast, something that defined our place in the cosmic web. And the next clue would reveal just how large that structure truly is.
As astronomers traced the motion of galaxies farther and farther outward, the picture became stranger. The Great Attractor was not acting alone. The galaxies falling toward it were not approaching from random directions. They were arriving along preferred paths. Long, filament-like streams of galaxies stretched across space, guiding motion like invisible channels. This wasn't chaos. It was structure. To understand what they were seeing, scientists turned to the largest maps of the universe ever created, three-dimensional surveys that plotted not just where galaxies were, but how they moved. These maps revealed something breathtaking. The universe was not evenly filled. It was organized into a vast cosmic web. Galaxies clustered along enormous filaments. Those filaments intersected at dense nodes, and between them lay immense voids, regions almost completely empty of matter. On the largest scales, the universe looked less like scattered islands and more like a network of glowing threads suspended in darkness. And motion followed that structure. Galaxies didn't drift freely through space. They flowed. They streamed along filaments, pulled by gravity toward the densest nodes. The Great Attractor was one such node, but it wasn't the only one. As scientists followed the flow lines backward, they realized something profound. Our entire local region of the universe, dozens of galaxy clusters, thousands of galaxies, was moving together, not as individuals, but as a single coherent system. This system was enormous. It spanned over 500 million light-years, and it had a name, Laniakea. The word means immeasurable heaven, and it was chosen carefully. Laniakea is a supercluster, a structure so large that it defies everyday intuition. Inside it lie familiar places, the Milky Way, the Andromeda Galaxy, the Virgo cluster, all bound together by shared motion, all flowing toward a common gravitational basin. At the heart of that basin lies the region we once thought of simply as the Great Attractor, but now it was clear. The Great Attractor wasn't a single object. It was a gravitational low point inside a much larger landscape, like a valley in a mountain range, and galaxies were rivers flowing downhill. This realization changed everything. The Great Attractor was no longer just something pulling us. It was part of the architecture of the universe itself. But the more scientists understood its place in the cosmic web, the more unsettling questions emerged. Because gravity depends on mass, and mass depends on matter. And when astronomers added up all the visible matter in Laniakea, it still wasn't enough, not even close. The observed galaxies, trillions of stars across thousands of systems, accounted for only a fraction of the gravitational pull required. Something else was contributing, something invisible. To explain the motion, scientists had to assume that most of Laniakea's mass was not made of stars, gas, or dust. It was made of dark matter, an unknown form of matter that does not emit light, absorb light, or reflect light. It reveals itself only through gravity. Current estimates suggest that dark matter makes up about 85% of all matter in the universe, which means the galaxies we see are merely decorations. The real structure is hidden. The filaments guiding galaxy motion are not built from stars. They are built from dark matter, a scaffolding that formed shortly after the Big Bang. As normal matter cooled, it fell into these invisible channels, lighting them up like lanterns along unseen roads.
The Great Attractor, then, may not be a place where galaxies gathered by chance. It may be where dark matter gathered first, and where visible matter simply followed. But this raised a deeply unsettling thought. If dark matter defines the universe's structure, then what we see isn't the universe as it truly is. It's only the surface. And the deeper forces shaping cosmic motion remain largely unknown. Even worse, when scientists examined motion beyond Laniakea, they found that the flow didn't end there either. Galaxies beyond our supercluster were moving toward even larger structures, even deeper gravitational basins. The Great Attractor was not the bottom. It was part of a cascade, a hierarchy of poles stretching across billions of light years, which meant one thing: the universe is not drifting apart gently. It is being sculpted, guided, pulled into patterns we are only beginning to understand. And the next discovery would reveal just how massive these hidden structures truly are, and how little control galaxies, including our own, actually have.
By this point, astronomers were forced to accept an uncomfortable truth. What they could see was not enough. The galaxies, the clusters, the glowing gas between them, all of it combined accounted for only a small fraction of the gravitational pull shaping cosmic motion. When scientists calculated how much mass was required to produce the observed galaxy velocities, the numbers refused to balance. They were missing most of the universe. To understand why, astronomers looked at gravity itself. Gravity is honest. It doesn't care what something looks like. It doesn't care whether it shines. It responds only to mass. And when galaxies bend light, distort space, or accelerate faster than expected, gravity is telling us something is there, even if we cannot see it. One of the most powerful tools used to reveal this hidden mass is gravitational lensing. When light from distant galaxies passes through massive regions of space, gravity bends that light. The images appear stretched, warped, sometimes multiplied. By measuring these distortions, scientists can map mass directly, including invisible mass. When they applied this technique to the region around the Great Attractor and the larger Laniakea supercluster, the results were stunning. The mass distribution did not match the light distribution. The strongest gravitational regions were not centered on the brightest galaxies. Instead, they aligned with vast, invisible structures, dark matter halos, filaments, concentrations far denser than anything made of stars. In some regions, visible matter made up less than 10% of the total mass. The rest was unseen. This explained why the pull was so strong, why entire clusters were drifting together, why the Great Attractor exerted influence across hundreds of millions of light years. But it also created a deeper mystery. If dark matter dominates the universe, then the universe we perceive is not the real framework. It is decoration. Stars are lights hung on an invisible structure we cannot touch, see, or directly detect. And the Great Attractor may be less like a monster hiding in the dark and more like a shadow cast by something far larger. To visualize this, imagine the universe as an ocean. Galaxies are floating debris on the surface. Dark matter is the deep current beneath. We see the movement at the surface, but the force comes from below. And those currents are ancient. They formed shortly after the Big Bang, when tiny fluctuations in density were amplified by gravity. Over billions of years, those fluctuations grew into the cosmic web, the filaments, the nodes, the voids. The Great Attractor sits at one of those nodes, a convergence point where dark matter density reaches a local maximum. Everything nearby flows inward. But here's where it becomes unsettling. Dark matter does not clump like normal matter. It passes through itself without friction. It doesn't collide. It doesn't slow down, which means once these structures form, they are incredibly stable. The Great Attractor is not temporary. It is not fading. It is part of the universe's long-term architecture, and we are inside it. Our galaxy is not choosing where to go.
It is being carried, dragged along by gravitational forces established billions of years before the Earth even existed. This realization changed how scientists think about cosmic motion. Galaxies are not independent travelers. They are passengers, bound to invisible highways shaped by dark matter. And those highways lead somewhere. But exactly where? When astronomers extended their maps even farther, they found something even more surprising. Beyond the Great Attractor lies another massive structure, even larger, even distant, known as the Shapley Supercluster. It may exert an even stronger pull on surrounding galaxies than the Great Attractor itself, which raised a troubling possibility. What if the Great Attractor is not the destination, but merely a waypoint, a bend in the current, a funnel leading towards something even larger? If so, then our motion, the motion of our galaxy, our planet, and everything we know, may be part of a journey far grander than we imagined. And the deeper scientists looked, the clearer it became. The universe is not simply expanding, it is flowing, and we are caught inside the stream. The next question was unavoidable. If dark matter shapes everything, what happens when these currents collide? And what does that mean for the ultimate fate of structures like Laniakea and the galaxies trapped within it?
When scientists realized that galaxy motion followed invisible currents, a new question emerged. Currents don't exist in isolation. They meet, they merge, they collide. And when they do, the results reshape everything downstream. On the largest scales, the universe behaves less like empty space and more like a landscape carved by gravity. High regions where matter is scarce, deep basins where matter pools. Galaxies don't choose their destinations. They slide downhill. And the Great Attractor sits inside one of these gravitational basins, but it is not alone. Astronomers discovered that multiple large-scale flows converge near our region of the universe. One stream moves toward the Great Attractor. Another points toward the Shapley Supercluster, located over 650 million light-years away. Shapley is one of the most massive structures ever observed. It contains tens of thousands of galaxies. Its total mass is so large that it distorts galaxy motion across an enormous volume of space. Some researchers now believe that what we call the Great Attractor is actually influenced by Shapley itself. In this view, the Great Attractor is not the ultimate source of motion. It is part of a chain reaction, a stepping stone in a gravitational cascade. This explains something puzzling. When scientists modeled galaxy motion, assuming the Great Attractor alone was responsible, the math still didn't fully work. The pull was slightly off, the directions were subtly misaligned. But when Shapley was included, the equations snapped into place. It was like discovering that a river's bend makes sense only when you see the mountain range beyond it. This means our entire supercluster may be moving toward a region far beyond what we can easily observe. And that movement is slow, imperceptible on human timescales, but relentless. At hundreds of kilometers per second, galaxies drift for billions of years. Over cosmic time, that motion reshapes the map of the universe. Clusters collide, galaxies merge, star formation surges and fades. These flows determine which galaxies thrive and which are torn apart. In regions where streams converge, collisions become more frequent. Gravitational interactions heat gas, trigger bursts of star formation, and feed supermassive black holes. The densest nodes of the cosmic web are violent places, not calm, not static. They are engines of change. The Great Attractor's region shows signs of this turbulence. X-ray observations reveal vast clouds of superheated gas, tens of millions of degrees hot, trapped by gravity. Such temperatures can only arise from extreme compression and collision.
evidence that matter there has been piling up for billions of years. But there is a limit to what gravity can do. Dark energy, the mysterious force driving cosmic expansion, is also at work. It pushes everything apart, so the universe is engaged in a tug of war. Gravity pulls matter together, dark energy pushes space apart. And right now, on the scale of superclusters, gravity is still winning. The attractor exists because gravity has not yet lost. But it will not win forever. As the universe continues to expand, distant regions will eventually slip beyond gravitational reach. The cosmic rivers will slow, flows will thin, and the universe will fracture into isolated islands of matter. Understanding structures like the Great Attractor helps scientists predict how and when that transition will occur. It tells us how long gravity can resist expansion and how the large-scale universe will change. But it also forces a humbling realization. Our galaxy's future is not determined locally. It is shaped by forces far beyond our immediate surroundings. For billions of years, the Milky Way has been drifting along invisible currents toward destinations written into the universe's structure itself. And that raises a final, unsettling thought. If gravity defines these paths so precisely, what else might be hidden in the currents, and what might lie at the deepest basins we have yet to discover?
By now, astronomers had mapped the flow of galaxies across hundreds of millions of light years. They understood the direction, they understood the speed, they even understood the structure guiding the motion. But one problem remained. They still couldn't see the destination clearly. Even with infrared surveys, X-ray telescopes, and radio observations, large portions of the Great Attractor region remained obscured. The Milky Way blocks nearly 20% of the extragalactic sky. Stars, dust, gas. Together, they form a thick veil that hides what lies beyond. This limitation matters because gravity does not act locally, it accumulates. And if there is something even larger beyond the Great Attractor, its influence may already be shaping motion we attribute to nearer structures. To test this, scientists turned to indirect methods. They studied the cosmic microwave background, the faint afterglow of the Big Bang. This radiation fills the universe uniformly, or at least it should. But when astronomers measured it precisely, they found a subtle anomaly, a dipole pattern. One side of the sky slightly hotter, the other slightly cooler. This temperature difference corresponds to motion. It indicates that our entire local region is moving relative to the early universe at roughly 627 kilometers per second. This motion aligns with the direction of the Great Attractor, but not perfectly. There is a residual component, a mismatch that suggests additional gravitational influence, something farther, something larger. This is where the mystery deepens, because beyond Shapley, beyond Laniakea, lie regions we cannot fully map. Distances become too great, galaxies too faint, uncertainty increases, yet motion persists. Clusters far beyond our supercluster show correlated velocities, as if they too are responding to a deeper gravitational landscape. This has led some cosmologists to propose that we are only seeing part of a much larger structure, a supercluster of superclusters, a hierarchy extending beyond current observational limits. If true, the Great Attractor is not exceptional. It is typical, just one node in a vast, repeating pattern. This challenges our sense of scale, because at that level, individual galaxies become irrelevant. Even superclusters lose significance. Only the largest flows matter, and we are passengers within them. But there is another possibility, one that unsettles even seasoned astronomers. What if the motion we observe is not caused solely by matter at all? What if the universe itself is slightly uneven? If the early universe contained large-scale asymmetries, regions of slightly higher density, those imprints could still be influencing motion today. This would mean the Great Attractor is not just a structure, but a fossil, a remnant of conditions set shortly after the Big Bang.
In this view, galaxies are not falling towards something newly formed. They are continuing a journey that began nearly 14 billion years ago, still responding to ancient imbalances frozen into space-time. If that is true, then mapping the Great Attractor is not just about understanding gravity. It is about understanding the universe's birth, why matter clumped where it did, why structure formed the way it did, and why motion continues along paths laid down in the earliest moments of existence. At this scale, certainty disappears. Data becomes sparse. Models diverge. But the implication is clear. The Great Attractor marks the edge of what we can confidently know. Beyond it lies a frontier where observation fades into inference, where gravity speaks but light does not. And the universe reminds us of a simple truth. No matter how far we look, there is always something pulling from beyond the horizon.
By the time scientists reached this point, the question had shifted. It was no longer just what is pulling us. It became why this direction at all. Because if the universe were perfectly uniform on large scales, motion like this should cancel out. Pulls from all directions should balance. Yet they don't. Our region of the universe has a preferred direction of motion. That should not happen easily. Standard cosmology assumes the universe is isotropic, the same in every direction when viewed on large enough scales. The Great Attractor challenges that assumption. To investigate, cosmologists examined the largest possible data set, the structure of the universe itself. They compared galaxy distributions across billions of light years. They studied temperature fluctuations in the cosmic microwave background. They analyzed large-scale bulk flows, coherent motions of matter spanning enormous distances. And what they found was subtle, but persistent. There may be large-scale anisotropies, small departures from perfect uniformity, not dramatic enough to overthrow cosmology, but significant enough to matter. Some studies suggest bulk flows extending farther than current models predict, flows too large to be explained by known structures alone. This led to a controversial idea. What if the Great Attractor is not simply a massive region, but part of a cosmic imbalance, a slight asymmetry in matter distribution left over from the early universe? In the first fraction of a second after the Big Bang, quantum fluctuations were stretched across space by inflation. These fluctuations seeded structure. Most were tiny, but if even one was slightly larger than average, it could imprint a directional bias lasting billions of years. In that case, galaxies are not falling toward a newly formed structure. They are drifting along gradients established at the universe's birth. The Great Attractor would then be less like a mountain and more like a slope the universe has been sliding down ever since. This idea is difficult to test because it requires measurements at scales approaching the observable universe itself, and beyond that we cannot see. But hints exist. Some anomalies in the cosmic microwave background, such as alignments nicknamed the axis of evil, suggest preferred directions. These observations are debated. Some may be statistical flukes, others may be artifacts of data processing, but they refuse to disappear completely, and they point loosely in the same general region of the sky. If these hints are real, they suggest something profound, that the universe is not perfectly symmetric, that it remembers its beginnings, and that the Great Attractor is not just a local feature, but part of a larger story written into space-time itself. This raises a deeper philosophical question. If motion on the largest scales is inherited from the universe's earliest moments, then our position is not random, not chosen, but inevitable. Our galaxy formed where matter happened to collect, and once formed, it was carried along paths laid down long before stars existed. The universe did not arrange itself for us. We emerged inside a flow already in motion. And that realization changes how we think about cosmic destiny.
Because if the universe has preferred directions, then the future may already be biased as well. And the Great Attractor may be pointing not just to a place, but to a deeper rule governing how reality evolves. The next question is unavoidable. If gravity and ancient structure guide motion so strongly, is there any scale where randomness truly exists? Or is everything, from galaxies to ourselves, riding currents we never chose? At this point, the Great Attractor stops being an abstract idea, because we are not observing it from a distance, we're inside it. The Milky Way is not stationary, it is not drifting freely, it is moving. Along with the local group, along with the Virgo cluster, along with tens of thousands of galaxies bound together inside Laniakea. Our galaxy is traveling through space at hundreds of kilometers per second, not because of a single nearby object, but because of the combined pull of structures spread across hundreds of millions of light years. This motion is smooth, stable, predictable, which tells us something important. The forces shaping it are ancient. They have been acting for billions of years. If the Great Attractor were a recent event, a sudden collapse or violent formation, the motion would be chaotic. We would see turbulence, random directions, abrupt changes. But instead, we see coherence, a steady flow. This means the gravitational landscape around us has been in place since long before the Sun formed, before the Earth existed, before life emerged. Every orbit in our solar system, every revolution of the Milky Way's spiral arms, all of it has unfolded while our entire galaxy has been quietly drifting along a cosmic current. And nothing in our daily experience reveals this. The motion is too smooth, too uniform. There is no cosmic wind, no sense of speed. Space itself moves with us. This highlights something deeply counterintuitive. Motion on cosmic scales does not feel like motion. There is no universal reference frame, no absolute stillness. Everything moves relative to everything else. The Great Attractor defines one such reference, not because it is special, but because it is massive enough to shape motion over enormous distances. For the Milky Way, this motion has consequences. Over billions of years, trajectories matter. Clusters that share similar velocities remain bound. Those that drift apart fall out of contact forever. The path our galaxy follows determines which future mergers are possible, which neighboring galaxies we will encounter, which regions of the universe will remain accessible. In the far future, as dark energy accelerates expansion, these flows will stretch. Eventually, distant clusters will slip beyond our cosmic horizon. Light from them will never reach us again. The Great Attractor's influence will fade, not because it weakens, but because space itself expands faster than gravity can act. When that happens, Laniakea will fragment. Its galaxies will become isolated islands. The cosmic river will dry. Understanding the Great Attractor tells us when that future begins. It gives astronomers a clock, a way to estimate how long large-scale structures can resist expansion, and how long galaxies like ours will remain part of a larger whole. But it also reframes our perspective. We often think of the universe as a backdrop, static, passive. In reality, it is dynamic, shaped by invisible forces, and we are participants in that motion. Even now, even as you listen, the Milky Way is being carried, quietly, relentlessly, along a path written into the universe long before we were here. And that raises one final unsettling idea. If our motion is inherited, if our direction is not chosen, then perhaps the same is true at every scale. And the Great Attractor may be only one example of a deeper rule, one that governs not just galaxies, but the unfolding of reality itself.
By now, the Great Attractor has stopped being just a destination. It has become a clue, a sign that the universe may not be as passive as we once believed. Because when motion aligns across such vast distances, it suggests coordination, not intention, not consciousness, but structure with consequences. On the largest scales, gravity doesn't just pull objects together, it organizes motion. It creates preferred paths. And once those paths form, everything that comes later must follow them. This idea forces scientists to reconsider something fundamental. Is the universe simply expanding and cooling? Or is it also directing its own evolution? The cosmic web suggests the latter. Matter flows along filaments not randomly, but efficiently. Energy dissipates into predictable configurations. Structures form where gravity can lower the universe's overall energy state. In this sense, the universe behaves like a system seeking balance. Not static balance, but dynamic equilibrium. The Great Attractor represents one of those equilibrium points, a place where matter has accumulated because it was statistically inevitable. Given enough time, gravity always wins locally, and once a basin forms, everything nearby falls in. This doesn't mean the universe has a plan, but it does mean outcomes are not arbitrary. Given the same starting conditions, similar structures would always emerge. This realization connects the Great Attractor to something much larger, the arrow of time. Time moves forward because entropy increases. Systems evolve from less likely states to more likely ones. The cosmic web is entropy expressed on the largest scale. Matter spreads out, but also clumps, not paradoxically, but necessarily. The Great Attractor is entropy's footprint, a natural consequence of how matter and gravity interact over billions of years. And that means its existence was never optional. It was unavoidable. From that perspective, our motion toward it was determined long before stars existed, long before galaxies formed, long before observers appeared to ask questions. We are not falling toward the Great Attractor by chance. We are following the most probable path available. This idea unsettles many people because it challenges free motion, randomness, even cosmic freedom. But it also brings clarity. The universe is not chaotic at its core. It is lawful, even beautiful in its inevitability. Yet this understanding opens a final, darker question. If structure dictates motion so strongly, what happens when structure itself changes? Dark energy is accelerating expansion. In the far future, it will overpower gravity on large scales. When that happens, cosmic flows will break apart, basins will empty, filaments will thin, the universe will stop organizing itself. And when that occurs, the Great Attractor will cease to matter, not because it disappears, but because nothing can reach it anymore. It will remain frozen in an ever-expanding sea of space, a monument to an era when gravity still ruled. Understanding the Great Attractor, then, is not just about where we are going, it is about when. It tells us we live during a special time, a narrow window when large-scale structure still exists, when galaxies still share destinies, when the universe is still connected. And that may be the most profound implication of all, because it means our ability to observe, map, and understand the universe exists only briefly, in cosmic terms. We are witnesses during a fleeting chapter, watching the universe while it is still flowing, still shaping itself, still revealing the forces that guide it. And the Great Attractor is one of the clearest signatures of that process. Before going any further, something important must be made clear. The Great Attractor is not a single object. It is not a supermassive black hole. It is not a tear in space or a cosmic anomaly violating physics. Those ideas are tempting, but they are wrong. The Great Attractor does not consume galaxies. It does not pull faster than gravity allows, and it does not override cosmic expansion. Instead, it represents something far more subtle,
and far more realistic. It is a region of space where matter density is higher than average, high enough to create a gravitational basin, high enough to influence motion across immense distances, but still governed by the same physical laws as everything else. This distinction matters because misunderstanding the Great Attractor leads to a deeper misunderstanding of the universe. The universe is not driven by singular catastrophes, it is shaped by accumulation, small imbalances amplified over time. The Great Attractor formed because slightly more matter ended up in one region than another. Gravity did the rest. Over billions of years, that imbalance deepened. Galaxies fell in. Clusters merged. Dark matter concentrated. No explosion, no event, just slow, inevitable growth. This is how the universe builds everything. Stars, galaxies, superclusters. Nothing dramatic at first, only persistence. Another misconception must also be addressed. The Great Attractor is not pulling the entire universe. It influences a vast region, yes, but beyond a certain distance, cosmic expansion dominates. Galaxies far enough away are moving too fast for gravity to overcome. They will never fall toward it. The universe is not collapsing inward. It is still expanding. What we are seeing is a local effect on an enormous scale, and this actually makes the discovery more important because it shows us exactly where gravity still wins, exactly where structure still forms, exactly where the universe transitions from connected to isolated. The Great Attractor marks a boundary between influence and freedom, between gravitational order and cosmological escape, and that boundary is moving. As dark energy accelerates expansion, fewer regions will remain bound. Superclusters like Laniakea are among the largest structures that will ever exist. No larger gravitational systems will form in the future, which means the Great Attractor is not just a feature of space, it is a fossil of a particular cosmic era, an era when gravity still had time to organize matter on the grandest scales. We live inside that era, but it will not last forever. In the distant future, observers in other galaxies will not see the Great Attractor at all. It will fade beyond the horizon. Its influence will become undetectable, and the universe will appear empty, quiet, and still. Understanding what the Great Attractor is not helps us understand what it truly represents. Not danger, not doom, but structure, order emerging from chaos, and a reminder that even the largest forces act slowly, silently, patiently. And that brings us to the final question. If the Great Attractor is a product of inevitable structure, what does that say about our place inside it?
By the time we reach this point, the Great Attractor no longer feels like a mystery hiding somewhere in space. It feels like a mirror, because what it ultimately reveals is not just where galaxies are going, but what it means to exist inside a universe that is always in motion. Nothing we have discussed is abstract. Every layer of motion is real. The Earth moves around the Sun moves through the Milky Way orbits within the local group. The local group falls toward the Virgo cluster. Virgo drifts within the Laniakea supercluster, and Laniakea flows along invisible gravitational currents shaped by dark matter and ancient structure. There is no final anchor point, no absolute stillness, no cosmic place where motion stops. Everything is nested inside something larger. This realization quietly dismantles one of our deepest intuitions. We tend to imagine the universe as a stage, vast, empty, and static, where events happen. In reality, the universe is not a stage. It is a process, and we are inside that process. The Great Attractor shows us that even on the largest scales, the universe is not frozen. It is evolving, slowly, relentlessly, following paths carved billions of years ago. What makes this unsettling is not the speed, It is the inevitability. Our galaxy did not choose its trajectory, it inherited it. The matter that formed the Milky Way was already moving before stars existed, before planets formed, before life emerged. The atoms that now make up your body once drifted through space along these same currents. They were carried into galaxies, forged inside stars, scattered by supernovae, and reassembled into worlds, all while the entire structure they belonged to was quietly flowing toward a gravitational basin it would never quite reach. In that sense, the Great Attractor did not shape just galaxies. It shaped the conditions that made complexity possible. And that reframes our place in the universe. We are not passengers observing motion from the outside. We are participants within it. Even our perception of time is shaped by this motion. Because cosmic structure evolves slowly, it creates the illusion of permanence. Galaxies feel eternal. Clusters feel fixed, but they are not. They are temporary arrangements, transient patterns in a universe governed by expansion. The Great Attractor exists only because gravity still has time to work, but that time is limited. Dark energy is accelerating the expansion of space, and expansion changes everything. As the universe grows faster, gravity loses its ability to bind distant regions together. Flows weaken, connections break. In the far future, superclusters like Laniakea will no longer function as coherent systems. Galaxies will become isolated islands. Light from distant regions will fade beyond reach. The cosmic web will thin until it disappears from view. Future observers, if any exist, will not see the universe we see. They will see a quieter cosmos, empty, still, deceptively simple. They will not detect the Great Attractor, not because it never existed, but because its era will have passed. That makes our moment extraordinary. We live during a brief window when the universe is structured enough to be mapped, yet young enough that those structures still interact. We can trace motion across hundreds of millions of light years. We can detect invisible matter through gravity. We can reconstruct the universe's large-scale architecture. This ability is temporary. Cosmic knowledge has an expiration date, and that may be the most humbling implication of all. The Great Attractor reminds us that understanding the universe is not guaranteed. It depends on timing, on where and when observers emerge. We exist at a moment when the universe is readable, when its history is still written across the sky, and when its future is still unfolding in ways we can measure. There's also a quieter emotional truth here. The Great Attractor does not threaten us. It does not doom us. It does not pull us toward destruction. Its influence is gentle, smooth, predictable. It will never arrive. We will never collide with it. The motion we experience is real, but the destination is conceptual. What matters is not where we are going, but the fact that we are part of a larger flow, that nothing exists in isolation, that even on the grandest scales, the universe is interconnected. This challenges the way we think about significance. We often measure importance by size or power, but the Great Attractor suggests a different metric. Significance comes from participation, from being embedded in something larger than oneself, from existing within a system that evolves even if it does not notice us. The universe does not revolve around life, but life arises within the universe's motion, and that is enough to give meaning. The Great Attractor is not a monster in the dark. It is a reminder that the universe has a history, that it has direction without intention, that it carries matter, energy, and information along paths shaped long before awareness emerged. And yet, here we are, able to trace those paths, able to ask why they exist, able to recognize that we are not separate from them. We are made of the same matter, bound by the same forces, carried by the same currents. The universe is vast,
Its structures are temporary, its forces are patient, and for a brief moment in cosmic time, we are here to witness it, not standing still, but moving with everything else.